The crash test dummy has been a staple in the safety equipment manufacturing industry. Many of today's newest innovations require safety, and since we cannot test things on actual human beings, a dummy is the second best alternative. While all models are wrong, some are useful, and such an example is the crash test dummy. The test dummy is used from roller coaster harnesses to space flight testing and to automobile crash tests. The ultimate goal of the dummy is to imitate injuries that would be sustained by an actual human. Therefore, its weight and dimensions must be roughly the same as a regular sized human. We chose to model a toddler's head. For our head, we used model styrofoam heads to imitate the shape and size of an actual head. The weight must be around 2.3 kgs to 5 kgs. So we used rice, coins, Jaden's orange peanut lacrosse balls, iron weights, and slime for a total mass of around 3.1 kgs, meeting our expectations of imitating a toddler's head. However, the neck was slightly more tricky. The human head experiences a recoil whenever it is struck in the head with enough force. However, our styrofoam head came with a neck. Therefore, we sliced up the neck using an X-Acto knife to slide the neck into three pieces and used duct tape to keep the head nice and bendy. We then filled it up with slime. It also started creating this black brown solution that stained many people's hands, and we found out it was sodium hydroxide, which meant some of the materials we were using maybe wasn't ideal.
With the head and the neck done, this concluded our first iteration and we went to test it. The results came out pretty good, but the neck was still too stiff as the head was tumbling off the table. To stabilize it from the back, we put a heavy object which imitates a car seat headrest. Nevertheless, the neck of the first iteration still did not replicate a real human neck. A real human neck exhibits elastic deformation and provides controlled rotational movement due to muscles, vertebrae, and soft tissue. In our dummy, however, the neck structure was overly rigid, resisting angular motion. This stiffness leads to a poor distribution of torque and forces causes the head to fall over the table instead of recoiling. Force equals the mass times acceleration, given by F equals to ma. As a result, the head accelerates, and because the neck couldn't flex to absorb or redirect the force, the entire force transferred straight through the structure. No dissipation, no softening, just raw motion. As the head moved forward or sideways, its center of mass shifted closer to the edge of the table. Once the center of the mass crosses the edge, gravity takes over. This makes the torque unbalanced, and once that happens, the system can no longer stabilize itself. Therefore, our first iteration met the weight and the size criterion, but realistically, it was not on point.
To fix this issue, we redesigned the neck structure in our second iteration using springs and duct tape. First, we increased the space between the parts of the neck, allowing for greater angular displacement between each segment. By increasing the distance, the neck can bend through larger angles, mimicking the rotational and bending ability of the human neck. Next, the spring we used provided our neck with the ability to undergo elastic deformation similar to a human's neck. Finally, the duct tape keeps everything together while also being a flexible material that allows for some damping, as while the human neck can rotate easily, it can't rotate too much as muscle tissues prevent it from rotating. Our second iteration was more realistic than the first, with the head demonstrating recoil due to the neck now being able to rotate. However, at times the neck would still not stay in place, so we needed to find out how we can keep the head still and not tumble around.
For our final iteration, we introduced a large wooden board as a stable base frame to anchor the neck structure and prevent unwanted translational motion of the entire dummy. For all our tests, the neck would always fall down after getting hit by the water bottle and wouldn't stay upright. We chose to use a flat and very wide wooden board for the base to help stabilize the head. This also prioritized neck movement and flexibility when measuring trials compared to the whole head moving. We are hoping that the dummy wears a seatbelt. The board allows us to define an axis of rotation and mitigate sliding and toppling. To mimic the rocking motion of a human head during a collision, we put duct tape on both sides of the head, acting similar to shoulders, while also providing additional damping so the head doesn't rock too much.
For the neck, we added pool noodle material, which provides compressibility and elasticity while keeping the head nice and sturdy.
The material is soft and flexible and is also able to spring back into shape just like a neck.
Using pool noodle material for the neck is more realistic than a traditional string, as metal spring follows Hooke's law, which is F is equal to Kx, meaning that the more you pull a spring, the more it pushes back in a very consistent linear way.
However,
a human neck does not behave
that way and doesn't apply force in such a linear way. The pool noodle behaves more like actual soft tissue, as it shows gentle resistance at first and gradually increases its force, which better simulates how human neck muscles stretch and absorb energy in a crash.
Alright, so we decided to test out if it was all secure. So we would put it upright and see if anything would spill out. However, as you can see, a lot of the rice and the corn spilled out, meaning that now we have to apply a new layer of tape. And that is what we're going to be doing now. Thank you.